Hello, everyone. My name is Chris Rossbach, and I am the CTO of Katana Graph. And today I'm going to give a talk that gives you an overview of the underlying technology behind Katana Graph's graph intelligence platform. And to set the agenda for the talk, let me just outline a few of the highlights I want to hit. I want to give you an overview of sort of the high-level vision behind Katana Graph, what we're trying to achieve in terms of the infrastructure we're making available within the community. I want to frame the subsequent discussion of how Katana is actually built in terms of the design principles behind the system. And then once I've articulated some of those design principles, I'll dig into some of the lower level components, in particular, what is the data model, the communication model, and the execution model that make Katana able to provide a super high performance scale-out graph intelligence platform. So with that agenda in mind, let me press on and give you a sense of what we're trying to accomplish. What is the high-level vision? So at Katana, with our graph intelligence platform, what we're really trying to do is enable programmers to have a single machine programming in the small abstraction over very, very large unstructured graph data. So concretely, we want programmers or users to be able to think about and ask questions of and gain insights into their unstructured data or their graph data by writing simple code in a familiar managed language, for example, Python, in an IDE such as Jupyter, and then have the runtime and the platform and compilers and all of the infrastructure provided by Katana figure out how to make that simple ergonomically expressed computation execute at super high performance in a scale-out cluster environment. And the way we go about realizing this vision is by assembling a stack of components that looks roughly like this. This is a fairly detailed and rich view of what's going on at Katana. But roughly speaking, there are four important layers here. At the very top, there's what we call the intelligent workspace layer. I think of that as essentially the programming front end. That is the way that the programmer will interact with the system. And at this layer, we support multiple ways of interacting with the system, either through Python or through OpenCipher or through C++. And at the second layer, we support multiple domains of graph computing. It's actually important to stop and dig into what each of these are, because historically, each of these domains has required a different and slightly specialized type of graph computing engine to support it. And what we do at Katana is use a single engine to support all of them. So graph querying is a domain in which, I'd say roughly speaking, you're asking questions about the structure of your graph. You're asking about what paths are present and what elements are connected by what paths. So a very, very common example is looking for connections between people in a social network and what people are connected on the way there. For example, does there exist a path from me to you that does or does not go through some other mutual friend or acquaintance? But these are problems that require graph traversals, and they are somewhat different in structure from problems that I would call graph analytics, which are problems that compute global properties of an entire graph. And we'll typically do so by iteratively touching every part of the graph until some convergence property is reached. So classic examples of graph analytics algorithms are things like PageRank, breadth first search, betweenness centrality, and so on. Graph mining is a domain in which we're asking questions about what patterns are present in a graph. How many triangles are there? Can we enumerate them? Is one of the most simple and canonical problems in this space. And among the more complex and perhaps more applicable ones are things like frequent subgraph mining. What is the most common subgraph up to size n in this particular graph? And then the final domain that we support at Katana is an emerging one, and one that I think is probably the most important in this space, and that is graph AI. And this is a label that we've applied to the sort of broad class of algorithms that have emerged at the intersection between machine learning, AI, deep learning, and graph. So things like graph neural networks, graph convolutional networks, graph transformer networks, and so on. So all of these are computing idioms that involve graphs, which can enable a user or an organization, an enterprise, or whoever to quickly gain insight into large volumes of data that they previously did not have insight into. And before Katana, these were all domains that were typically supported by specialized graph computing engines. What we've done at Katana is use a single scalable distributed graph engine to support them all and do so in a way that provides orders of magnitude benefit in terms of performance and efficiency. And there are a number of key elements to realizing this vision, 4 of them, in fact, that I'm going to dig into over the course of this talk. It's how do we partition graphs in a way that enables a distributed set of resources to efficiently communicate over them, and that's a technology called CUSP. What do we do at each host in that cluster to efficiently compute over partitions of the graph, and that's a technology called Galois, which is a local graph computing engine. And then how do we orchestrate or get all of these different hosts in a cluster to efficiently collaborate and communicate to compute locally over partitions of the graph to gain insights into a global graph. Okay, so these 3 components together, CUSP, Galois, and Gluon, comprise the graph engine. And that graph engine rests on a foundation that is our data abstraction. It's called a resilient distributed graph, or an RDG. And that's supported by both an in-memory representation and an in-storage representation, which are very similar. And I'll spend some of the talk talking about how that abstraction is realized in both of those locations. So with that basic overview of what the components are, I want to take a step back and talk about the design principles that went into building Katana Graph so that some of the design decisions should sort of hopefully make sense within that context. So key graph design principles that went into the Katana Graph intelligence platform are program in the small, execute in the large. I think this one is largely non-controversial, right? This means letting a programmer write economic, ergonomic, small scale, easy to reason about code that can then be executed on large scale infrastructure. And this has a number of implications, but ultimately it boils down to providing a managed front end that encapsulates distribution and scale. And if you look at the sort of the research literature over the last 15 to 20 years, as well as systems that have emerged in industry, ranging from sort of early entries like MapReduce and Hadoop to more recently technologies that have evolved through Spark to become Ray and so on. This is a charter that I think is shared by all of these systems, as well as Katana's system, that is specialized in Katana in a way that enables interoperation with those other systems at the same time as it is specialized to be very fast for unstructured data. The second design principle I want to bring out is the following. Be a platform rather than a database. This is something I'll spend a few slides trying to unpack in a few moments. But the high-level implication of doing this is that it has a certain sense of being more general than just a database, but there are a number of other things that fall out from this, like the necessity to be in multilingual environment. What do I mean multilingual? I don't mean sort of multilingual in the human language sense. I mean it in the machine or the human talking to machine language sense. We need to support multiple front-end languages. It further implies that we want to prioritize data flow functionality over database features. So Katana Graph supports a fully featured graph database, but the platform itself is capable of quite a bit more. And I'll talk about how and why that is the case in the coming slides. And it also implies the use of an exposition of a shared log. And actually, this may not be sort of a fundamental implication. This may be more of a design decision, but I think it's incredibly important to being a platform. And I'll spend quite a bit of time on this. Specializations for graphs, perhaps not surprisingly, since I've already intimated that this will be the case. The Katana system has a number of specializations that occur both at the storage layer, secondarily at the communication layer, and then at the execution model layer that make it possible to be very efficient for graph data. And the final principle that I'm going to articulate, but not spend time on in this talk because I don't go on and on forever, is that we want to virtualize resources, but only do so when necessary. So the Katana Graph Intelligence Platform relies on what I'll call a highly hybridized virtualization architecture that uses different techniques at different layers. For example, the deployment strategy is heavily containerized at the same time that our strategy for composing environments that use accelerators like GPUs relies on specializations at the hypervisor layer. So if you want to know more about that, please go check out katanagraph.com or reach out to me, and I'm happy to talk about it. So with these design principles in mind, let's dig into each of them in turn. And talk about or unpack what the implications are. So in terms of programmability, in terms of this, program in the small and execute in the large kind of charter, this is really boiling down to something that I think we've all learned over and over again in the past decades in the computing ecosystem, which is that ease of use is really the most important thing, right? It's a first-class design constraint. We really want to realize this vision that where a person can think about a large graph very easily in a small scale environment and yet take advantage of large scale resources. And what this turns out to in the context of supporting multiple graph computing domains is also support for multiple front-end managed languages. So if I can recall your attention back to this stack diagram that I showed early on, it has these 4 computing domains. In each of these graph computing domains, I would say the lingua franca is different, right? So in particular, in say graph analytics and graph AI, in particular AI, I would say Python has become sort of the de facto standard for writing workloads in this space, which means that supporting a Python front end, not just for orchestrating a graph engine, but also for programming low-level algorithms is going to be critical. At the same time, in the graph query space, much of the front-end programmability story follows straight from what we have been doing in the relational database community for decades, which is building a DSL, which is a query language. So Cypher is a query language for graph that is one among a panoply of new query languages that look a little bit like SQL, but have a bunch of syntax that enable you to talk about and reason about graph structures. This is something that needs to be supported by Katana as well. And of course, there's a whole HPC community, high performance community, scientific computing community that may want to use Katana Graph, for which C++ and also to some extent Python are really the idioms of choice. And Katana supports front-end language access in these areas as well. So critically, Jupyter is really the IDE that forms the basis for interacting with Katana Graph. And the key technologies that now enable us to support all of these different front ends boil down to sort of advanced compiler technology and automated code transformations. So compiling each of these front end languages, either cross-compiling it to a native backend or through some IR, is the fundamentally enabling transformation that allows us to do this. So I also want to talk about another facet of programmability, which is that programmability is not just about application code. I think that's the thing that comes to most of our minds first when we think about programmability. We want programmers to be able to write their algorithms as quickly and easily as possible. But ultimately, programmability is not about application code alone. It's also about a number of other dimensions like deployment. And Katana's system adheres to a number of best practices that many of us have come to understand and use in the distributed computing community around infrastructure as code. But it's also about interoperation with other systems. So we believe very strongly at Katana Graph that graphs are wonderful. And when you have unstructured data or data that is structured but is clearly structured as a graph computing framework is absolutely what you want to use. But many data pipelines out there in the world, if not most, may have some steps for which graphs are the right idiom and many steps for which graphs are not the right idiom. And making it very easy for programmers to compose pipelines that use graph computing for the phases where graph fits and other frameworks such as Spark or Ray when graph is not the right idiom. That's also a first-class design constraint for Katana that results in exposition of things I would call orchestration APIs, things that make it possible to use it as a single step in a data flow system, as well as a strategy for dealing with ETL and ELT strategies that are more ELT steps that are more about supporting common interchange idioms than about supporting schema mapping technologies and supporting adapters to do import and export. But I'd like to spend some time unpacking this contrast that I brought up earlier between data flow and databases. And in order to do that, let me first spend a little bit of verbiage, at least trying to define what I mean. So this will be a little bit informal, but hopefully you'll get the key ideas here. A database, I'll claim, is a piece of software and associated infrastructure that allows a programmer or a user or an organization, whatever, to manage and mutate a corpus of data, right? Typically by gathering it into some abstraction like tables and then supporting some language over which you can express questions or mutations to that data. A data flow system, on the other hand, is something that allows a programmer to compose DAGs, directed acyclic graphs, or actually perhaps even just directed graphs of arbitrary computation, right? So to give you an example, up here on the right, I'm showing you a data flow program that involves something that takes as input some large graph and runs PageRank on it. And the output of PageRank is consumed by a Louvain clustering algorithm and some cipher query C and so on, right? So what's happening in a data flow system is each of the nodes in the data flow graph represents computation. Each of the edges represents input-output dependencies or data transformations that have to occur between those computations. Okay, now, what is important about this distinction is ultimately they are both sort of Turing complete, but they have different fundamental properties when it comes to the accessibility and the amount of friction that takes place when data moves in and out of the system, as well as their generality. Right? So a database tightly couples data with computation. You import your data, you put it in tables, and you can express some computations in SQL. As soon as you need to express something that is not well served by SQL or perhaps by stored procedures, you have to export data from your database and use some other kind of computation. I would argue that in contrast, a data flow system is much more loosely coupled, tends to natively separate storage and computation, and is able to perform essentially arbitrary computations because the data flow architecture itself says nothing about what computations can occur at each node. Now, both of these idioms, as I've said, are Turing complete, which means that you can support either of them on top of the other. You could build a data flow abstraction on top of the database, or you could build a database abstraction on top of the data flow system. And it is our view at Katana that building a data flow abstraction on top of a database is hard because it requires expensive and painstaking ETL steps, the addition of an orchestration layer to manage a graph, schema mapping, and potentially even extra provisioning to deal with providing different frameworks to run each stage of a data flow graph. By contrast, a data flow system that implements a database abstraction is, I've said easy here, which may belie actually some of the heavy lifting that needs to be done, but ultimately I do believe it is fundamentally relatively much easier and requires a few things like a carefully designed storage layer and a shared log that I'll talk about later, but it's a lot less, it's a much lower friction system. And Katana, the Katana Graph Intelligence Platform, is ultimately a data flow system that supports a complete graph database abstraction. And the benefits that derive from taking this approach are that we're able to deliver critical database, expected database features like ACID transactions, but it's also sort of designed natively for easy composition and orchestration. It's designed in a way that anticipates integration with other data flow engines like Spark or Ray. And I would argue that also challenges around ETL and ELT are simplified because they're designed and tailored to anticipate transformation along data flow edges. So that was a lot of abstract argumentation around the distinction between data flow and databases. Let me sort of step into the more concrete domain of showing you how the different components of the Katana Graph architecture collaborate to form a data flow system. And one key player in this is, of course, the client, right? This is a piece of software that runs where the programmer or the user is trying to run computations. This is typically a Jupyter notebook where someone might write some Python algorithms to orchestrate the graph engine or send cipher queries to our system. And that client will talk through a library to a component called the Katana service. And that service will in turn speak to a number of other components to orchestrate computations. It will talk to a component called a state store. It will work with a shared log, which you'll see me argue is a critical component here, as well as interacting with a fleet of hosts that run graph worker processes. And within each of these worker processes, we're going to talk to a global object store. So these are roughly the players. Let's dig into what each one does. The Katana service is, as the label says, a scheduler, but it also serves as a sort of a common surface for API requests It's ultimately the component that creates and tracks jobs, even though it may store its state elsewhere. The workers themselves, right, graph worker hosts, these are gang scheduled MPI process groups, each of which reads and writes partitioned graphs, which we call RDGs, resilient distributed graphs. And I will talk later in the talk about exactly what RDGs are and how they work together. But to give you a sketch of it, they're supported by the storage layer, and they form the fundamental data abstraction of Katana by providing the abstraction of an immutable graph, right? So a single instance of the sort of Katana platform may comprise some number, one or greater graphs, and each of those graphs will be versioned. So once you've created a graph, you can never change it again, but you can have the abstraction of a mutable graph by maintaining a history of mutations captured as versions. Each of those versions can have some number of views, which represent different partitionings of the graph, either for different numbers of hosts or under different graph partitioning policies, or both. And I'll spend a slide talking about that later on in the talk. But ultimately, these form a highly flexible and super efficient way of storing graphs in a way that is customized toward the execution model of the system. The state store. This is the component that fundamentally enables things like availability for the Katana service, right? Katana needs to be highly available, which means that any component needs to be able to fail at any time. This means that all of the state that is required by the Katana service, things like what operations are in flight, the namespace of the storage system, what workers are alive, and so on. All of this is state that needs to be stored in a way that is backed by a consensus protocol. So our state store currently is backed by an etcd instance and stores scheduler state, storage namespace, and so on. And the final component I want to call out is the shared log, which is a write-ahead log that provides sort of an ordering and recovery service. It is also the foundation of all our fault tolerance, crash consistency guarantees, as well as the fundamental building block for ACID transactions. Ultimately, the shared log is the source of ground truth. So if you've worked in this space or built any kind of distributed computing framework or data flow engine, I would say most systems that have emerged in the community over the last 10 years or so have analogs for most of these components. But the shared log is I would argue, a distinguishing feature that enables us to provide a strong database-like guarantees, despite being a highly flexible data flow engine. So let me dig into the shared log concepts a little bit. The key idea here is that Katana wants to support an abstraction of shared graphs in an environment where the shared log is the ground truth. And what this means is that shared data like graphs or other metadata about the system are sort of materialized in the system as a view, potentially, usually in memory. So data structures such as the graph itself will have an in-memory materialization, and it's materialized by playing forward over a history of ordered updates that are stored in this shared log. Now, this has a number of nice properties, because if you can make the log itself highly available, fault tolerant, and high performance, many of those properties sort of adhere directly into the upper layers of the software stack. This makes the shared log ultimately the final source of persistence for our system. It makes it the source of availability. It makes it the source of elasticity, because adding more nodes is simply a matter of adding them to the graph worker pool and telling them to play forward the shared log. It's a source of atomicity and isolation, because transaction protocols based on logs, these are well understood and have been researched for quite some time. There are a lot of I would say options or alternatives, design alternatives in this space. The particular protocol that Katana uses is from the Tango paper in SOSP from 2013. I strongly encourage you to read it if you're interested in that. But this also enables us to provide atomicity and isolation across multiple graphs or multiple data structures. So this is the foundation of our transactional subsystem as well. So, final thing, right? Unlike many systems in this space, which I would characterize as comprising components that do a lot of point-to-point communication through RPCs, the shared log also provides a central place to sort of roll forward and learn what's happened in the system, which means that appends and reads on the shared log can replace messaging in many parts of the Katana system. So key benefits to wrap up around the shared log design is that the shared log itself does all the heavy lifting for many of the distributed systems properties that have proved very difficult to implement in systems of the past, such as persistence, consistency, atomicity, and isolation. It also provides us a nice portability mechanism because a shared log implemented on top of cloud storage services like S3 are sort of very easily portable to other cloud storage services as well. It dramatically simplifies fault tolerance because the transaction protocol will tell us exactly what operations have committed and what have not. As I said in the previous slide, elasticity is greatly simplified because adding and removing workers requires less coordination. And then ultimately, I would argue that exposing the log through other APIs is a key enabler for interoperation. So for example, supporting ETL or incremental ingestion can be implemented by allowing other services to append to the shared log and do not necessarily require the instantiation of all the other components of the service, most notably the worker hosts. So this is a nice property of the log as well. So hopefully this has been an informative tour of the sort of the design principles behind Katana. Let me dig in a little bit more component-wise to talk about how each of these are specialized in a way that allow us to provide a cloud-native data platform that is specialized for graph intelligence. And to, again, frame that discussion, I sort of want to swap in some state by reiterating aspects of the Katana stack that boil down to our charter of supporting these multiple domains of graph computation, query, analytics, mining, and AI, based on a single graph engine on top of a resilient distributed graph abstraction. So as I said previously, the graph engine itself composes a partitioning piece called cusp, which answers questions of how do we take a large collection of unstructured data and turn it into a graph that is partitioned or sharded over all of the hosts in the cluster. The Galois compute engine is the component that answers the question of what do we do at each of the hosts in the cluster to contribute to getting the answer of a graph query or an analytics problem or an AI or a mining routine. And then the gluon component is the piece that allows all of the hosts running a Galois compute engine to communicate with each other and synchronize across BSP rounds to eventually arrive at the right answer. Now the RDG, or the Resilient Distributed Graph Abstraction, that is supported by both in-memory and in-persistence views, are also fundamental and interoperate with these in ways that are very, very clearly specialized to our charter of computing over graphs. So let's dig in to the ways in which we are specialized to be a graph intelligence platform. These boil down to methods that specialize our data model. How do we partition the graph to make it efficient to compute over it? What is the execution model? And what is the communication model? Each of these have a clear tie-in to the graph computing space. So I promised to talk more about resilient distributed graphs, and I'll do so here. If you're familiar with Spark, you'll instantly recognize the homage, which I feel is appropriate, to the RDD, the Resilient Distributed Dataset abstraction supported by it. The RDD is very similar in spirit to many of the sort of partitioned distributed collections that are supported by other engines like Dryad Link. But what is different between all of these frameworks and what goes on at Katana is that the partitioning strategy for an RDG will not partition the data into completely disjoint chunks over which we will exercise data parallelism, but rather we'll partition it into overlapping chunks over which we will exercise BSP parallelism that will synchronize across rounds. And I'll get into that when I talk about the execution model a little bit more. But to give you a sense of what's going on to enable this at the storage layer, the RDG itself is essentially a collection or a history of versioned, partitioned views of a distributed graph. And these views are application optimized. So what does that mean? We have found that the partitioning policy that you use to shard a graph across multiple hosts tends to have a workload-dependent impact on performance. One algorithm may work well with one policy, but not so well with another, and so on. So what we're trying to do underneath the covers of the RDG is allow the storage engine to manage this problem automatically by choosing different views and capturing different views that represent different partitionings and automatically providing them on request or on demand to the graph engine itself. In terms of what's going on in the format itself, The topology is stored efficiently as CSR. If you're familiar with sparse matrix techniques, you'll know about CSR as compressed sparse row. It's a very compact way of storing sparse data that has a very, very good locality for certain types of traversals. The CSR itself forms an index into the property data for the labeled property graph abstraction supported by Katana. And that property data itself is captured essentially in columnar format using Parquet. So this gives us a nice integration story into modern data lakes, but ultimately boils down to efficient compression and encoding schemes. It also enables our graph engine to support efficient and flexible distributed graph computing because these multiple versions are also captured in a memory efficient delta encoded way and also support transparent on-demand repartitioning to deal with demand for different partitioning policies or different numbers of hosts. So again, I've preceded something that will be hopefully much more concrete with something very abstract. Here's the concrete view of this idea. And it's an idea embodied by the component called CUSP. CUSP is short for customizable streaming partitioner. And this is a component that can take a large corpus of unstructured data and turn it into multiple partitions that can be computed over using multiple hosts in the graph. And the key difference here, the differentiating factor, is that we will partition a graph into subsets that may overlap, right? Which means if you look at this diagram here in the middle of my screen, I can get my mouse back up, what you'll see is that this graph that comprises vertices A through I and the edges is partitioned into partition 1 and partition 2, and you'll see that some of the vertices appear twice. For example, F is circled here in a solid line indicating it's a master replica. It's also appearing in partition 2 as a mirror replica. So what is the difference? The difference is something that boils down to these invariants here on the right. The partitioner works by first assigning each node uniquely to a host and then preserving the invariant that all edges have to connect some replica nodes on the same host, right? So if we put this edge here that connects F and G on this host, this means that F and G need to be present in some replica form in both partitions, okay? Now, this translates to the impact that a node can have multiple replicas. In this case, one will be the master. It's in charge of collecting all the updates after a computation round, and the rest are mirrors. So what are the features and important aspects of doing this? One is something that is not on this slide, is that it enables very efficient BSP style communication, as you'll see when I get to that slide. But two, it enables sort of very, very low friction partitioning and customizable partitioning, because it enables a programmer, either someone working at Katana or somebody using the graph engine, to express their own partitioning policies in terms of a very, very small handful of callbacks, ones that specify which node has the master replica, and for each edge, which host has that edge. So let's move on and talk about how we compute at each host in the cluster. And this is based on the technology we call Galois, which is the local graph computing engine. And it is optimized to compute over unstructured data in a sort of data-centric programming model. What this means is, if you're familiar with parallel patterns libraries based on data structures, Galois is exactly this in a way that is specialized for graphs. So Galois supports a number of sort of pre-parallelized data structures, most notably and obviously graphs, work lists for composing work list algorithms based on graphs, as well as large arrays. And the programming model itself is based on parallel loops with a work stealing runtime. It is very fast, not just because it's carefully designed and has some good, well-implemented data structures, but also because the runtime itself does a number of optimizations, like NUMA-aware memory allocators that will always use huge pages as much as possible, custom thread pool management, and so on. Now, very, very importantly, a key differentiating sort of technology for Katana Graph is the fact that while we have a well-encapsulated set of APIs for calling analytics and invoking mining and AI APIs, we also expose these interfaces directly through Python and C++. So programmers can extend the system and implement their own graph algorithms. Gluon, as I said earlier, is the substrate that is used to communicate between different hosts in the cluster. Each host is running the Galois compute engine and computing over some partition that is computed initially by cusp. Gluon is essentially an extension that enables round-based bulk synchronous parallel computation over each of those partitions. And there's a bunch of text here that I'll get back to, but I find it easiest to understand in terms of this diagram on the right, in which we have a two-host cluster comprising graph workers 1 and 2, each of which perform some computation by first reading their partition of the graph, which is determined by cusp, and then performing in a loop a local computation based on Galois, followed by a synchronization of all of the replica nodes in the graph using Gluon. And the reason this can be super fast is that it takes advantage of well-exercised and time-tested MPI technologies, as well as all reduce. Right? So we'll tend to reduce from mirror replicas to master replicas and broadcast from master replicas to mirror replicas. And MPI implementations of this are very fast. This also enables partition-aware communication that can exploit structural and temporal invariance of the graph, as well as a set of optimized distributed global accumulators that appear over and over again, particularly in graph analytics algorithms like add and min and max, average and count. So Gluon itself is very developer friendly because it abstracts away all the details of distributed execution. Right? It's forming that, it's a key enabler of this single machine abstraction over multiple machines operating on a distributed graph. So with that, I want to touch on one final area of specialization, which is how Katana Graph uses the shared log to support transactions, right? So as I said in the previous discussion about the shared log design, the log itself is ultimately the source of ground truth for the system. And Katana uses a transactional update protocol over RDGs to ensure that ultimately all operations performed by Katana have transactional semantics, whether they are unit operations that have implicit transactional semantics or explicitly grouped by the user operations, operations that are explicitly grouped by a user into a transaction. So this is a nice extension of previous shared transaction log ideas that also extends very naturally to support exposed data version. So by combining an operation log with this history of RDG versions, developers can easily access and revert to earlier versions of an RDG. And this is useful for a lot of sort of compliance-related things like audits, disaster recovery, things like rollback, empirical concerns like reproducing experiments, and then ultimately time series analysis that may compare one version of a graph in the past against a more recent version. And while Katana does not yet support time travel, this is very much on our near-term roadmap and will be supported soon based on the key techniques in the transaction log. And to just give you a basic flavor of how this works, I've got a diagram that shows a transaction log that has appends over time going downward. And I've got a transaction on RDG-A and a transaction on RDG-B that are concurrently interleaved onto the transaction log in a way that preserves concurrency, but provides a total order over transactions, but also, most importantly, emphasizes this idea that the log itself is the source of ground truth. For example, this transaction on A may begin with a version 0 of the RDG that was imported from some bulk import source like CSV, and produces a version, a new logical version, and perhaps that version is only materialized in memory and never actually persisted to the storage layer. This is fine. That transaction is, that mutation is still persistent because it is trivially reproducible by playing the log, which is persistent, forward to replay that operation. So this is the foundation of a lot of performance-focused optimizations like group commit that can help make the Katana intelligence platform very, very fast. So this is completes my tour of kind of the key highlights that I wanted to bring out about the technology behind the graph computing intelligence platform that we've been building at Katana. And in conclusion, I just want to touch on a few highlights. Katana Graph Intelligence Platform is a highly programmable, interoperable, scale-out graph processing framework that enables multiple domains of graph processing, It functions as a fully featured graph database, and at the same time supports a number of forward-looking domains like data flow and graph AI, as well as graph analytics and graph mining. And we spent most of this talk touring some of the key enabling technical insights, such as a shared log design that lets us support a database on top of a data flow engine, a graph specialized data model and graph specialized partitioning strategies, as well as programming, execution, and communication models that are specialized to graphs. So I want to thank you for your attention. I hope you've found the information illuminating, and I look forward to hearing your questions and talking with you about the materials. Thank you.